for extraction, will the efficiency go up or go down? That is the question that is asked. Okay, so same amount of solvent, but it is now divided into 4 parts and you are doing 4 extractions. Okay, it is like a 4 stage cross flow system. So what happens? The equation gets slightly modified. The equation will become XR is equal to XF divided by 1 plus E raised to the power n, where n is equal to 4, correct. Now again we can calculate your extraction efficiency. E is given by 2.5 because you have now the quantity of the solvent is divided by 4. Okay, so it is become, instead of E being 10 in the previous case, E is 10 in the previous case, now E has become 2.5, correct. So the equation is XR is equal to XF is 25 divided by 1 plus 2.5 raised to the power 4. So you get XR as 0.166. So you are starting from 25 and after 4 stages of extraction with 1/4 the amount of solvent you are able to extract 99.34% of the protein. You see in the previous case when you put all the solvent into one stage you are able to extract 91%, but when you divide it into 4 equal parts and do the extraction in 4 distinct stages you are able to recover 99.3% of the protein. That means a multiple stage extraction is always efficient, even if you are using less solvent, multiple stage extraction is always efficient. So that is the main takeaway from these two problems. So instead of using a large amount of solvent and putting it in one stage, you divide that solvent into many stages, many portions, and then perform an extraction. That means mixing, equilibration, separation, then mixing, equilibration, separation. Like that, if you do it in multiple stages it is much more efficient. That is why in labs we do not add all the solvent in one go and try to extract. We always put little solvent, extract it, remove the solvent, again add little solvent to the feed or the broth, again extract it, and by doing that we are actually achieving a much higher separation efficiency rather than putting all the solvent in one lot. Okay. Now let us look at another problem. This is a multi-stage counter current extraction. That means the solvent is flowing in one direction, your feed or the heavies is flowing in another direction. That is why it is called a counter current. The solvent when it is entering it is devoid of any solute. So the concentration of solute in the solvent layer is 0. Now feed is entering at a solute concentration of XF and the raffinate that is leaving on the other end has a concentration of XR. If you remember, this is the equation which I showed a few classes back, where XR and XF are related by this particular relationship, where you get E. E is the efficiency of extraction. We will assume that the efficiency is constant in each stage and the quantity of solvent or feed does not change when it moves from one stage to another stage. That means the miscibility of the solvent and the heavy is 0. Okay. So the E remains constant in each stage, okay, and n here in the denominator is the number of stages. So this is the equation for a multi-stage counter current process. So if you remember the previous equation for a system where you have cross flow, and if you look at this counter current, both are very different type of equations. Okay. Now we want to extract 99% of a protein in a continuous counter current extractor. The rate of heavy is 450 liters per hour, okay, that is feed, and it is extracted with 40 liters per hour of solvent, that is S. Partition coefficient is given 60. So how many stages do you require? Again E is given by this formula, S into K by F. S is the solvent rate, K is the partition coefficient, F is the feed rate. So if I substitute all these I get E as 5.33. Now you take this equation, I want to extract 99%, right. So XR by XF will be 0.01. that means only 1% of the solute is left behind in the raffinate. Then I substitute all these terms here. Once I substitute all these terms, I get n is equal to 2.6, right. That means I need 3 stages, I need 3 countercurrent stages to perform this extraction. That means if I want to extract 99% of my solute, using a solvent of 40 liters per hour flow rate and a heavy flow rate of 450 liters per hour, I need at least 3 stages. So the most important condition or the assumption here is the streams that are leaving each stage are in equilibrium. That is very important assumption in all these type of design calculations actually. So with 3 stages I will be able to extract 99%, and the main advantage of the continuous flow system is the extraction can be performed in a continuous fashion. Okay, we looked at different types of problems. Now let us look at something different, another type of extraction concept. This is called supercritical fluid extraction. It is becoming very popular, especially in the area of food, nutrition, nutraceuticals, natural product chemistry and natural product based drug design and so on actually. For example, your instant coffee, if you want to remove the toxins, if you want to remove the caffeine present in the coffee, now people are resorting to supercritical fluid extraction. The main advantage of supercritical is you do not have to use high temperature. That means chemicals or nutritious material or nutraceuticals or vitamins that are present will not get denatured or deactivated. That is the main advantage of supercritical. So you can retain the aroma will not get affected because of changes in pH or changes in temperature, flavors will not get affected. So supercritical is becoming a very big area in the food and flavor industry. Generally carbon dioxide is used as the solvent because it is available in plenty, it has got a very good critical pressure and temperature. So with the reasonably good values of pressure you will be able to get a supercritical carbon dioxide. So it acts as a solvent. So a supercritical fluid is neither a gas or a liquid, so it is in between. So it has got very interesting properties which is made use of in the supercritical fluid extraction. So there are certain definitions which you need to know, and the most important definition is critical temperature and critical pressure. So what is a critical temperature? The temperature above which a liquid cannot exist, that is called a critical temperature. So the vapor pressure of the substance at its critical temperature is called critical pressure. So at these temperature and pressures, that means at critical temperature and pressure you will have a substance and that exists as supercritical fluid. Why carbon dioxide is used? As I said, it has got a good, reasonably good supercritical temperature and pressure, number 1 and 2, and it is non-toxic and it is not flammable, it is also non-hazardous. So that is why carbon dioxide has become extremely popular. And another advantage is, as soon as you reduce the pressure, the supercritical carbon dioxide will immediately go into gas, leaving behind your metabolite or aroma or whatever solute you are trying to extract. So that is the main advantage. Then again you can pressurize the carbon dioxide and convert it into a supercritical fluid. Sometimes other solvents are also used for supercritical process, like nitrous oxide, sulfur dioxide, ammonia, ethane, propane, butane, pentane and ethylene and so on. So the transport properties of solvents such as density, viscosity, diffusivity, thermophysical properties, heat capacity, latent heat of vaporization, all these are very important in an extraction process. and a supercritical fluid will have a less viscosity. If you compare it with respect to a normal liquid, supercritical fluid will have less viscosity, and it will also have very good diffusivity. That means this supercritical fluid can diffuse into materials, very small pores, and extract. So if I have a solid natural product and I want to extract the flavor or fragrance from that, then it can penetrate through small pores and then extract the flavor or fragrance. And also because it has got a low viscosity, the flow properties are also extremely good when compared to a normal liquid. So increase in pressure increases density of fluid and thereby the solvent strength also. So especially near the supercritical point, that means it is called the critical point, even when you change the pressure little bit, you see large changes in the density of the supercritical fluid. And also the latent heat of vaporization of solvent decreases for a supercritical fluid and almost becomes 0 at the critical point, because there is no phase transition. That means it is not going to become move from one phase to another. That is why the latent heat of vaporization becomes 0. And also the heat capacity of the supercritical fluid will be several times greater than the normal liquids. If you look at physical properties of gas, liquid and supercritical fluids, so as I said, supercritical fluids fall between gas and the liquid, and so it gets the advantages of gas, it gets the advantages of liquid, at the same time it discards the disadvantages of both these. If you look at density, for example, in grams per cc, gas densities are extremely small, 10 power minus 3. If you look at liquid, it may come up to almost 1, but supercritical will be in between that. If you look at viscosity, liquid viscosities are extremely high. So supercritical fluid viscosity is almost close to the gas. If you look at the diffusion coefficient, gas diffusion coefficients are very large, liquid diffusion coefficients are very small, supercritical diffusion coefficients are in between 10 power minus 3, whereas liquid diffusion coefficients are 10 power minus 5. So you get almost 100 times enhancement in the diffusion coefficient of a supercritical fluid. So it has got a very good viscosity comparable to gas, and the diffusion coefficient is much higher than of the liquid, and the density is also much higher when compared to the gas. So you see that it has got the good points from liquid and good points from the gas. That is why supercritical fluid has become a very important technology for food industry and flavor industry. Many advantages are there. So there are other alternate to liquid extraction using solvents such as hexane or dichloromethane, because when you use hexane, that has been a traditional chemical used in food and flavors, even in natural product chemistry, but what happens is some residual solvent will be left behind which may be very toxic, and if it is a food product, then you do not want toxicity present in your food, and then you are going to have environmental hazard, environmental contamination of these toxic hexanes or dichloromethane, and also you may have flash point and explosion hazards if you are using such low boiling solvents. So that way the supercritical fluid like CO2 is extremely good. It is not going to be left behind in the food or flavor, it is not going to be an environmentally contaminating chemical, because CO2 is present in plenty in our environment, and it does not have any explosion or flammable hazards, and the supercritical fluid containing CO2 is produced from the CO2 found in my atmosphere. So it is not also going to leave any carbon footprint. That way it is not going to add to the carbon dioxide already present in our atmosphere. So it is not going to create an extra greenhouse gas. So it is also approved by the Soil Association if you want to remove organic contaminants present in soil. and also CO2 is found in plenty when you go to a brewing industry, fermentation industry, because when you are fermenting sugars your CO2 is one of the byproduct. So, it is not creating any extra emission. So, industries where CO2 is one of the products can be located next to your industry which makes use of this CO2 for producing the supercritical fluid, which can be then used in the food and flavoring industry. So, we can change the selectivity by changing the pressure and temperature. For example, volatile oils can be extracted from a plant at a pressure of 100 bar, whereas if you are using a liquid like hexane, it may also remove lipids. So, supercritical fluid that way can be very selective. I can use CO2 at very high pressure to remove lipids alone, and I can remove phospholipids by just adding ethanol to the solvent. That means you are adding entrainer to this supercritical CO2. Speed is very fast because it is based on diffusion, and as I showed in a few slides back, the diffusion coefficients are very high as against a diffusion coefficient of a liquid solvent. There is no surface tension and viscosities because they are much lower than in liquids. The viscosity is much lower, almost close to gas. So, it can enter very small pores, it can enter matrix and matrices which are inaccessible by liquids. So, the speed of extraction is also very fast. If an organic liquid takes several hours to complete the extraction, if I use a supercritical fluid I can do it in 10 to 60 minutes. So, we are talking in terms of an improvement in speed by a factor of 3 or 4. But there are limitations also. So, if you are going to use very high pressure, that means your equipment also has to be very high pressure. That is one of the disadvantages. Your capital cost of a supercritical unit is high. So, you need to recuperate the capital cost, and CO2 is a non-polar and it has got a very limited dissolving power. So, cannot be used for polar solutes. Polar solutes means solutes which are hydrophilic in nature. So, that means you need to add some modifiers. Ethanol for example is used as a modifier. Generally if you are using for food grade, then ethanol is the only solvent that is allowed actually. But then if you are going to use ethanol at room temperature, ethanol will be in the liquid form, not like a vapor. So, if I bring after the extraction, if I bring the gases to room temperature and pressure, CO2 will become vapor, but ethanol will be left behind. So, that is a disadvantage of using entrainer. But then if you want to extract polar liquids or polar solutes or polar metabolites, then we need to add entrainers because CO2 is a non-polar material. This is a typical schematic diagram of a supercritical extractor system. Okay. So, we may have a CO2 tank, series of large cylinders containing CO2, then you have a compressor. Okay. I compress the CO2, then you pump. So, initially you have a CO2, it becomes a supercritical fluid after compression. Okay. Then it is pumped. You may need to heat depending upon the type of extraction operation that is being carried out. You may heat or you might not heat. Then this is where you have your solids matrix, natural product or any food material. The extraction takes place, and then this is called a flash vessel. So, the pressure is brought down to ambient condition, the CO2 goes as gas, and again it is collected back and recycled. So, the main advantage here is I can keep on recycling my CO2 except for very minimal losses. So, the solute here, if it is in the form of liquid at ambient condition, will settle down as liquid, which can be drained. So, it could be a flavoring or it could be a unwanted toxic chemical which you would like to remove from your food, for example like removing caffeine or from coffee or theanine from tea and the sort of toxic chemicals. So you are talking about 350 bar, so some of the design should be able to take care of this 350 bar. That is why the capital cost of this system becomes bit expensive, but you do have laboratory scale equipments for supercritical. You may have 500 ml extractor, 1 liter extractor going up to 5, 10, 100 liter extractor. So when we talk about 100 liter extractor, that means about 70-80% of the volume could be used to fill your solid end. Okay. So this is a typical schematic diagram of a supercritical unit, and of course because of the high pressure you may require extra alarms and extra pressure relief systems and so on in this particular system. Okay. Optimization is a very important study we need to do. What should be the pressure at which I get the maximum extraction efficiency. So if you are talking about extracting oils, I may go up in pressure, because if you take an oil extraction plant, then the quantity of CO2 used will be a significant cost and complete extraction might not be required. Even a yield of 70 to 80% is economical, and the most of the cost is because of the quantity of CO2 that is used actually. If you are talking about optimization, we need to also consider the improving the diffusion. So this can be achieved by increasing the temperature, assuming that the chemicals that are getting extracted do not get degraded at higher temperature. Swelling the matrix, so if you have a solid plant material or if you have a solid food product, by swelling it you can allow the fluid, supercritical fluid to enter through the interstices, small pores and so on. So you like to swell the matrix. Reducing the particle size, smaller the particle better will be the extraction, because it is you are talking about a fluid solid interaction, and any fluid solid interaction will be governed by the area of contact. So using smaller sized solids will always be good for extraction. So how do you swell the matrix? So we can increase the pressure of the solvent, we can add modifiers and so on, so that the solid matrix gets swollen. Even some polymers and elastomers can be swollen by carbon dioxide actually. So if you have polymeric material, the supercritical CO2 will swell that matrix. How do you maximize solubility? So we can use higher pressure. When you use a higher pressure, solubility increases. At pressures well above critical pressure, solubility is likely to increase temperature also. So if you are using very high pressure, then the supercritical CO2 temperature also may be very high. So you may have to cool, that means you need to put in a cooling system to cool the supercritical fluid. Sometimes addition of methanol or ethanol modifiers can increase solubility especially for more polar compounds, because as I said CO2 is a non-polar. So when I add a little bit of methanol and ethanol, then it is very good for polar compounds. Okay, when we talk about polar systems, nowadays supercritical water is also becoming very fancy, but the main problem with supercritical water is the pressures are extremely high when compared to CO2. That means the hardware design is a big challenge, number one. Number two, supercritical water is also very corrosive. So the material of construction of the material of the equipment also becomes very critical. So that is why supercritical water although is extremely good for removing polar solutes unlike supercritical CO2, but the pressures required are very high, the corrosion issues are also very serious. So we need to consider those aspects when we are designing supercritical water systems. So what are the extraction conditions for supercritical CO2? For example, I can the critical temperature is 31 degrees centigrade and critical pressure is 74. That means if I am above this temperature and above this pressure, CO2 will be in the form of a supercritical fluid, and I can process any system, and by modifying the pressure I can improve the solubilities, and I can modify the temperature to improve the diffusion coefficients, as long as the solids which you are trying to treat can agree or can allow this type of temperature and pressure. For example, if I want to decaffeinate coffee, or if I want to extract volatile oils or fragrance from plant or flower, 100 bar is enough. 100 bar is considered as a low pressure. Okay, so at 100 bar and ambient temperature, I can remove the volatile oils and fragrance from flowers and plant material, because here you do not want to increase the temperature, otherwise the fragrance will lose the fragrant molecules will lose their activity. Similarly, I can decaffeinate coffee at such low pressures. Main advantage here is I can reduce the pressure and convert the supercritical carbon dioxide into the gas, so there is no residual solvent left behind with the solute, so the solute will be 100% pure. So it is good for food and cosmetics and other similar industries. Cosmetic industry also loves supercritical, because in a normal cosmetic industry they used to use ethanol, pentane, ethyl acetate, that sort of solvent. So you need to select solvents which are not toxic to human. So using supercritical advantages, there are no solvents left behind, so the solute will be pure. So you are also carrying out the extraction at low temperature, that means you are carrying it out at ambient conditions, so there is no deterioration of heat sensitive components in the extract. That is another main advantage. In a CO2 system there is no oxygen coming into, that means you are not going to have oxidation of the extract. So practically there is not going to be any oxidation happening, rancidity happens because of oxidation, formation of peroxides and so on. So such things which normally are found in food products will be very absent when I resort to supercritical CO2 type of extraction. So there is no residual solvent left behind, you are doing it at low temperature, so thermally labile materials do not deteriorate, and there is no oxygen during the process, so there is no oxidation that is taking place. So these are the three main advantages of using a supercritical CO2. So what are the applications? The applications of supercritical CO2 is plenty in food and pharmaceutical industries as well, fragrance industry, cosmetic industry and so on actually. So we can use it for decaffeinating coffee and tea, that means the toxins in coffee and tea can be removed. We can use it for extracting fish oils, because fish oil is finding a lot of applications in some of the nutraceuticals type of area. So we can use it for extracting it. We can use it for extracting vegetable oils from, we can use it for extracting flavors, natural resources from plants, fruits, from flowers and so on, so which can go into a nutraceutical industry. So it is very advantageous there. Extraction of ingredients from spices and red peppers. So if one is interested in packaged food, we need to add lot of spices and condimonium. So, those type of material could be extracted using a supercritical type of approach. Extraction of fat from food products, even with the health consciousness, the entire population of the world would like to have food which have low fat content. So, there supercritical fluid extraction technology can be applied, so that the amount of fat present in the food is also much less. We can use it for fractionating polymeric materials. We can separate out polymers based on its molecular weights. So, if one is interested in separating out polymeric materials, more natural polymers as well as synthetic polymers based on molecular weight, low molecular weight content and higher molecular weight content polymeric material, then supercritical fluid extraction is a very good approach for that. Extraction from natural products, this is one area where it is finding application, especially if you are talking about drugs from natural products, drugs from phytochemicals. So, as you know, most of the phytochemicals will contain several different metabolites, maybe 20 to 50 different metabolites, and separating them and recovering the active ingredient or the most important component is a big challenge. If you use chemical methods, it may be impossible to separate out all these 20-30 fractions, and you may lose the activity because of the higher temperature. Again, supercritical fluid extraction technique can be used for separating out phytochemicals towards drug design. Supercritical fluid is also used in analytical technique, just like a normal high pressure liquid chromatograph, where you are using your mobile solvent for separating out various phases. We can use a supercritical carbon dioxide to separate the metabolites present in a mixture of components. The main disadvantage or the only point we need to consider is it is a non-polar liquid. So, it is like separation using a non-polar continuous phase. Okay. So, you can separate out a large number of compounds using the supercritical, and then by reducing the pressure we may be able to extract the complete pure component without any solvent present in that actually. So, that these are many advantages of a supercritical fluid system, both in the food, pharmaceutical, and when we talk about food, we are talking about the flavoring industry, nutraceutical industry, and healthcare products and healthcare industries.